Terminal velocity. Consider a spherical body falling through a viscous medium. Initially, it accelerates due to gravity. As the velocity increases, the retarding force, viscous force, also increases. When viscous force and buoyant force acting in upward direction becomes equal to the force due to gravity, the net force becomes zero and so does the acceleration. The sphere then descends with a constant velocity. This velocity is called terminal velocity. For dynamical equilibrium, viscous force plus buoyant force equals to weight of the body, as shown in the figure. This implies Fb plus Fb equals to mg, where F is the viscous force and Fb is the buoyant force, m is the mass of the body, the spherical body, and g is the acceleration due to gravity. This implies 6 pi eta a into Vt plus 4 by 3 pi aq sigma g equals to 4 by 3 pi aq rho g, where rho is the density of body, sigma is the density of liquid, a is the radius of a sphere, and eta is the coefficient of viscosity. Thus we have 6 pi eta a into Vt, where Vt is the critical velocity of the spherical body, equals to 4 by 3 pi aq into rho minus sigma into g. Hence Vt equals to 4 pi into aq into under bracket rho minus sigma into g divided by 3 into 6 pi eta into a equals to, thus we have Vt equals to 2 by 9 into a square by eta into rho minus sigma into g. This is the expression for critical velocity of a body falling, a spherical body falling in the liquid of density sigma. Now Archimedes' principle. A body wholly or partially submerged in a fluid is buoyed up by a force equal to the weight of the displaced fluid. The upward force is called upthrust or force of buoyancy. Buoyant force or upthrust Fb equals to Vi into sigma into g, where Vi is the immersed volume of the body, sigma is the density of liquid, and g is the acceleration due to gravity. And consider the density of body is rho and density of liquid is sigma. Let h equals to height of the body and x equals to part of the body immersed in the liquid, and a is the base area of the body. Then Fv equals to Vi into sigma g equals to x into a into sigma into g. If body is wholly immersed, then x equals to h. Hence Fb equals to h into a into sigma g. Now apparent weight. Due to the force of buoyancy, the body immersed in a liquid loses its weight. The weight after loss is called apparent weight, is equal to the actual weight minus buoyant force. Hence apparent weight equals to m into g minus v into rho into into g. Or v equals to rho minus sigma into g, where v is the volume of the body, sigma is the density of the liquid, and rho is the density of the body. Example: the terminal velocity of a copper ball of radius 2 mm falling through a tank of oil at 20 degrees Celsius is 6.5 cm per second. Compute the viscosity of the oil at 20 degrees Celsius. Density of oil is 1.5 into 10 to the power 3 kg per meter cube. Density of copper is 8.9 into 10 to the power 3 kg per meter cube. We have terminal velocity 2 into a square into under bracket rho minus sigma into g by 9 eta. This implies eta equals to 2a square into rho minus sigma into g by 9 into vt. Here given vt equals to 6.5 into 10 to the power minus 2 meter per second. A equals to 2 into 10 to the power minus 3 millimeter. Sigma equals to 1.5 into 10 to the power 3 kg per meter cube, and rho equals to 8.9 into 10 to the power 3 kg per meter cube. Using all value in the above formula, we get eta equals to 2 into 4 into 10 to the power minus 6 into 7.4 into 10 to the power 3 into 9.81 by 9 into 6.5 into 10 to the power minus 2. Critical velocity of a fluid. The maximum velocity of a fluid up to which it is steady called critical velocity. Velocity less than critical velocity, flow is steady. Velocity greater than critical velocity, flow is turbulent. Reynolds number. It is a dimensionless number whose value states about the nature of flow of the fluid, that is laminar, steady or turbulent. It is given as Re equals to rho into V into d by eta for flow in the pipe, where rho is the density of a fluid, V is the velocity of the fluid, and d is the diameter of the tube. Here we have Re equals to rho into V into d by eta equals to rho into multiplying V both up and down side, rho V square d by eta into V equals to A into rho into V square by d, V square into d by A into eta into V equals to A rho into V square by A eta V by d equals to inertial force by force of viscosity. Because A into rho into V square equal to A rho into V into V, A into rho into d delta x by delta t into V, A into delta x into rho into V by delta t equals to V, capital V rho into A equals to ma, where V equals to capital V equals to volume, A equal to acceleration, force equals to ma. Important point: flow is a streamline or laminar for Reynolds number Re less than 1000. Flow is turbulent for Reynolds number Re greater than 2000. When Reynolds number is between 1000 and 2000, the flow is steady, and at random it becomes turbulent. Flow rate: the volume of fluid flowing through the cross section of a pipe per unit second is called flow rate. It is denoted by Q. Let V be the velocity of the fluid, then length of cylindrical fluid flowing in time interval delta t is delta x equal to V into delta t. If A be the area of cross section, then volume of cylindrical fluid, delta V equals to A into delta x equals to A into V into delta t. Hence flow rate, volume flown divided by time interval. This implies Q equal to delta V by delta T equals to A into V into delta T by delta T equals to A into V, or A equals to, hence Q equals to pi into R square into V equals to pi into d by 2 का whole square into V equals to pi into d square into V by 4, where d is the diameter of pipe, cylindrical pipe, and V is the velocity of fluid in the pipe. Example: the flow rate of water from a tap of diameter 1.25 cm is 0.48 liter per minute. The coefficient of viscosity of water is 10 to the power minus 3 Pascal second. After some time, the flow rate is increased to 3 liter per minute. Characterize the flow for both the flow rates. Find Reynolds number. Solution: Q equals to pi into d square into V by 4. Hence V equals to 4 into Q by pi into d square. We have Reynolds number Re equals to rho into V into d by eta. Using the value of V in this, we have Re equals to rho into 4 into Q into d by eta into pi into d square equals to 4 rho Q by pi eta d. Now 1 liter equals to 1000 cc, 10 to the power 3 cc, 10 to the power 3 cm cube, 10 to the power 3 into 10 to the power minus 2 meter का cube equals to 10 to the power 3 into 10 to the power minus 6 meter cube equals to 10 to the power minus 3 meter cube. 1 liter equals to 10 to the power minus 3 meter cube, and 1 minute equals to 60 seconds. When Q equals to 0.48 liter per meter equals to 0.48 into 10 to the power minus 3 meter cube divided by 60 seconds equals to 8 into 10 to the power minus 6 meter cube per second. Hence Re, Reynolds number in this case, 4 into 10 to the power minus 3 kg per meter cube into 8 into 10 to the power minus 6 meter cube per second divided by 3.14 into 10 to the minus 3 Pascal second into 1.25 into 10 to the power minus 2 meter equals to 815, which is less than 1000, so flow is steady. Similarly, when Q equals to 3 liter per minute, we get Re equal to 5095, and it is greater than 2000, so the flow will be turbulent. That's all.